Purpose of the lab was to determine the mass of a black hole and the initial velocity of a spaceship that travels as close to it while still escaping the black hole, all via coding. The physics principles used are the decomposition of the momentum principle, the velocity update formula, position update formula, and gravitational force formula. The main result of this lab are the mass of the black hole and initial velocity of the spaceship listed below.
Here are the fundamental physics principles shown in this lab. First, the momentum principle decomposed into parallel and perpendicular components, which, as you can see, the parallel component of force is the dp dt pointed in the direction of the momentum of the object, and the perpendicular component of force is the magnitude of the momentum times the derivative of p hat, which is the unit vector, the derivative of the unit vector of momentum. And also we have the velocity update formula and position update formula derived from the momentum principle, as well as the gravitational force formula. Initial conditions for part 1 of this lab. Here you can see the gravitational constant, the mass of the star, which was given, and the time intervals between data points, which are the amount of seconds per day. Here you can see that in the first two lines contains the vector that holds all the x and y components of velocity that are calculated in the while loop below. This is the portion of the code where we calculate the mass of the black hole. We first start off by finding initial and final momentum, as well as calculating the final initial change in velocity and momentum. We then set Fnet equal to dp dt because that is the definition. And when we go on to calculate the parallel component of net force, which allows us to find the perpendicular component of net force because we just subtract the parallel component from the overall component, overall net force. We then find the mass of the black hole by rearranging the gravitational force equation. The mass of the black hole, which was yielded by this code, was 6.69 times 10 to the 33rd kilograms. And below you can see the shape of the orbit, which was yielded by this code as well. The path that the star follows around the black hole is an elliptical path, meaning that when the black hole has a larger force of attraction on the star, the closer it is to the black hole. According to the decomposition of the momentum principle, changes to the parallel component of force results in a change of speed, where changes to the perpendicular component results in a change of direction. These two ideas show why the star's momentum increases in magnitude as it moves towards the black hole and decreases as the star moves away from the black hole. Discrepancies in the mass of the black hole between each run may have originated from rounding values during each time through the loop.
Additional values of part 2 of this lab include the mass of the black hole calculated from part 1 and other various masses of the planet and the ship. All the way at the bottom you can see the x and y components of the ship's initial velocity determined by trial and error.
Next, we calculate the net force acting on the planet and ship by analyzing how all three of the black hole, planet, and ship interact with each other. So by that I mean we calculate the force of gravitation between all three of these objects and add them up together to determine the net force acting on a certain one. And then all the way at the bottom you can see we calculate the velocities and positions of both the planet and the ship using the velocity and position update formula along with the net forces that we calculated above. As said previously, the initial velocity of the spaceship was found to be negative 3.2 times 10 to the 7th in the x direction and 1.5 times 10 to the 6th in the y direction. This was found by the trial and error method, and of course it's velocity, so the units are meters per second. The reason that the ship is able to escape the black hole is that as the ship gets attracted closer and closer to the black hole, the gravitational force that the black hole exerts on the ship speeds the ship up. This is because the ship's momentum and gravitational force from the black hole are pointed in the same direction. This increase in speed allows for the ship to reach an escape velocity and break free of the elliptical path. Rounded values for the mass of the black hole as well as rough estimates for the initial velocity of the ship may have resulted in slightly inaccurate final result. What does it mean? Essentially the parallel and perpendicular components of rate of change of momentum and net force are equal. The difference is in this lab we are calculating the various components of the rate of change of momentum, and we then just assume that they're equal to the components of net force. What if initial velocity of negative 1.7 times 10 to the 6th meters per second in the x direction and with 7.0 times 10 to the 6th meters per second in the y direction get the spaceship to complete an orbit around the black hole without hitting the planet?